This conference will now be recorded.
All right. Our speaker today is, wait, did we lose Eric? Oh, no. Okay. Speaker today is Dr. Eric Ouyang. I hope I'm saying your name right, the last name right.
That's correct.
And from JSET, thanks to Swami and Michael for arranging this. Wait, I need to make you a presenter. Sorry about that.
Sure. Thank you.
He's going to be talking about thermals, and you take all the time you need. And then after that, Shahab, maybe we should just revisit our favorite die-to-die phi spreadsheet as well.
Okay. Let me check how do I share the screen. Give me 1 second.
Take your time.
Can you see my screen?
Not yet, no. Now you can, yes.
Okay.
I should have done this sooner. Sorry about that.
I'm trying to find my
We can see your
presentation file.
desktop. Yeah, we can see your desktop, and there you go. Now we can see the deck.
Okay. Hello everyone. My name is Eric Ouyang. The title of my today's presentation is a thermal reliability study of chip lab modules. Let me share a little bit the background of this presentation. JCET and the Meta platform, we actually one of the Meta platform engineer or manager invite me to work on this presentation together in 2021 OC Summit. And the title of the presentation is Thermal Consideration between monolithic die and the 2.5D and 3D packages. And after that presentation, I decided to publish a paper, and the paper was published in early this year at ITHM, and the title is Thermal Design of a Chip Lab Module Using Monolithic Die and 2.5D 3D packages. So this my today's presentation, the first part will be based on the presentation and the paper. And later this year, I'm going to present another paper at Interpack. And from slide 11 to 20, I will also share a little bit of this paper. Okay, this is the OCP presentation. Let me go through it quickly. Okay. For that presentation, we try to compare the thermal performance among various packages. If you see the below figures, you will see the monolithic die, MCM, 2.5D and 3D modules. All the dimension clearly shown on the images. Okay, and this slide from the table, you can see the detailed package dimension, die thickness, and also the powers of each module. To do the apple-to-apple comparison, we have to make sure the ambient temperature are same, and the volume, flow rate, and also the heat sink, everything are same, except the package configuration are different. And this is the simulation result. You can see that for the monolithic die, the junction temperature is about 89.1, and the 3D stack die, the junction temperature is 99, and this is for the 3D stack die, the junction temperature is higher, and this is reasonable. And for the option 1 and option 2, MCM and a 2.5D interposer, the junction temperature is 84, about 84. So it's in between the monolithic die and 3D stack die. And you can see also the case temperature. But this case temperature is a little bit, I think it's misleading because usually people define the case temperature, the location of the case temperature at the top center of the um, modulus. But the problem is that because we had several dies, so the physical meaning of this case temperature is not going to work very well if we try to use this temperature to define the thermal performance of the modules. Okay, let me move to the next slide.
Would you mind going back to the previous slide for 1 second? Not the
Sure.
one before this.
This
So
one?
all the MCM packages are smaller than the monolithic.
Okay, let me go back to this slide. So this is the monolith. You mean the total area,
So they're
right?
all the same 65 by 65 footprint, basically.
Yes. The
Oh,
all this is 65 by 65.
okay. And it's just that the MCM or the multi-chiplet packages take up more of the package area than the monolithic.
Yes.
But as far as the board is concerned, they all look the same.
Yes, because we want to do the apple to apple comparison.
Okay, thank you.
Sure. So I already shared this one, but let me repeat it one more time. So the simulation results shows that the junction temperature of the monolithic die is slightly higher than that of MCM and 2.5D packages. And a junction temperature of 3D stack die has the highest junction temperature. And the third bullet, as I mentioned, that the case temperature actually is not a good indicator if we try to use that one to define the thermal performance of the packages. So the next step is that um, is, besides the junction temperature, we also we want to understand how the dies on the MCM module will impact each other. Okay, and this is uh, and the fourth bullet basically I share you in the next slide. Okay, and this one uh, the monolithic die ideally is the best one, but monolithic die in general the manufacturing cost will be higher. And for the 3D stack die, same. The cost will be very high. Also, the manufacturing is going to be very complicated. So I believe right now most people will prefer to use either MCM or 2.5D in the poser. So the next one is that hotspot or allow max operation temperature of ASIC and a strength on MCM or 2.5D modules. The temperature distribution is one of the concerns we need to pay attention to. So for this reason, we decide to design a vapor chamber to control the temperature distribution. If you look at the bottom, you can these two images, you will see that on the acid die, the right side, you will see the red color. So which means the junction temperature is higher. So in order
Yeah,
to yeah,
quick question before you move on. So for the power, did you consider the uniform power distribution, or you consider, like a non-uniform power distribution for these cases?
for this one, we only consider the uniform power distribution.
Okay, so if you consider non-uniform, most likely your hottest spot location would be different, but
Yes.
the values that you got most likely should be close to what you presented today, right?
If we have the uniform power distribution, if for the if we put this the chiplet into a server, I think that the junction temperature will not change a lot unless your long uniform power distribution is very extreme. What I mean is that if you really all the power concentrate in a small area, then of course it will be different.
Right, right. Which could be a
For this
case.
one, for this study, we do not have the real circuit power distribution data. I mean the power map. So we don't do that. But we have a few customers. They provide us the real power map. Then we can model the hotspot location.
Yep, sounds good.
Yeah. So we decided to use the vapor chamber. So if you look at the bottom two images, the left one is without the vapor chamber. So you can see that the red color is concentrated at the right side. Let me show you this one. Yeah, something like here. You can see that there's a hotspot or maybe a temperature, a higher temperature concentration at the right side. So if you look at the right image, you will see that we design a vapor chamber at the right side of the heatsink base. Then you can see that the temperature is more uniform. The right image, you will see that this is one of our simulation data. With vapor chamber, the temperature gradient between the ASIC and the SRAM is about 20 degrees. Also, the ASIC temperature is 99.7. And when there's no vapor chamber, the temperature gradient is 26 C, and the ASIC temperature is 111 degrees. So vapor chamber can not only lower the temperature, but also mitigate the temperature difference.
Pardon my ignorance, but what is a vapor chamber?
Vapor chamber is okay. It's basically are you familiar with the heat pipe?
Yes.
Okay, basically it's inside is a easily vaporized liquid. So when it's heated, the liquid will be vaporized. So it will help dissipate the heat quickly, and you can imagine that inside the vapor chamber, the thermal conductivity will be very, very high. For example, copper is about 400. Conductivity is about 400, and the vapor chamber it will be around a few thousand, maybe 4,000, 5,000.
Thank you.
Okay. So the vapor chamber is used to to conduct the heat to outside heating base efficiently, and lower the overall temperature, and also the lower the temperature difference. Okay, let me move on to the next slide. So this slide concludes the presentation. So we know that from the presentation, we know that MCM and 2.5D interposer have better thermal performance compared to monolithic die and the 3D packages. And as I mentioned earlier, the case temperature is a misleading parameters. So when we do compare the thermal performance, we should not only consider the case temperature. And in order to improve the thermal performance, we can use, for example, a vapor chamber, and we can also use a leadless package. And of course, we can also use better thermal interface material. There are a lot of options.
Just a quick question on the vapor chamber again. You said
Sure.
vapor chamber underneath the ASIC. Don't you mean on top of the ASIC?
Inside the heatsink, Let me go to
Oh,
this.
inside the heat sink. Oh, right. Okay.
Yeah, yeah. For
Okay, so the
example,
copper piece is the vapor chamber. I got you. Okay, thank
yeah,
you. Thank
okay.
you.
And was the vapor chamber connected to ASIC or to both ASIC and DRAM?
For this case, we only have the. Let me go to this slide. So for this study, we designed a vapor chamber only on top of the ASIC.
Okay, I see. Okay. And since the ASIC temperature dropped, then like the DRAM would be or SRAM was the temperature of that one reduced.
Yes.
Okay. And the question.
I'm sorry. I was just going to say, is the SRAM on the top in this diagram, or is the ASIC on the top?
Okay. Let me go back to this here. Okay.
So the SRAM is on the top, is it?
No. For the MCM and 2.5D, the SRAM is as
yeah, I mean, I'm on about the 3D one.
The 3D is at the top, yes.
The SRAM is on the top, and so the SRAM is the coolest, and the ASIC is underneath. Also, you're showing the SRAM is smaller than the ASIC. Does that mean the heatsink only touches the SRAM and doesn't touch the ASIC at all, or is it a multi-byted vapor chamber?
The heatsink is big enough to cover everything, But what I'm trying, but for this, when we design the heatsink, it's only the area on top of the ASIC. We have the vapor chamber.
Oh, on the 2.5D. You haven't done the 3D one, or you haven't shown the 3D one in this presentation.
We don't do the 3D, but we did a 3D, but 3D doesn't have a vapor chamber.
Oh, okay, thanks.
So Eric, I have a question about this 3D. So basically, the way that obviously it like the for 3D connection between the chiplet is either through the macro bumps or through hybrid bonding, right? So how do you take into account the effect of the macro bump, and once it's hybrid bonded in your thermal models, right?
Mm-hmm.
How would you model them?
There are two approaches. The first approach that we can consider all the detailed features of the microbump, which means in the simulation we can model all the detailed bumps. Another option is that we use an effective material property to model the entire area. And for this study, we use the second approach. Take 3D stack die, for example. I think it's not going to make a big difference because all the dies are so close to each other. And actually, the silicon, the bomb have very good thermal conductivity. So they are very close to each other. So the SRAM and the ASIC, the temperature actually will be very close to each other because if you look at this image, they are so close.
Right. So technically, yeah, either lump model or the detail model, right? Detail one is expensive, obviously. You cannot model 15,000 or more, like a micro bump, just in case for some of the design. But like the lump model is one way. But if that's why I like in past, I've seen a study, or even ourselves, we consider that one like as a lump block, to represent that one. But my problem is always for hybrid bonding, right? So how would you, have you ever done any simulation to take into account of that layers? Like, we have the, let's say, silicon oxide as a dielectric plus the copper hybrid bonding, right? Would you add another layer to take into account of that interface thermal resistance in your model? So if you don't basically consider that one, every hottest spot temperature that you got on let's say top die would be imprinted on the the bottom die, right? So that's why to me it's a slightly the wrong approach to consider, right? So that's why I'm asking you, what would you do in case of the hybrid bonding, or what's the JSON approach here for hybrid bonding, thermal modeling of the interface between die to die in the case of hybrid bonding?
To be honest with you, we actually it's only me. Maybe my other colleague they have done the hybrid bonding. I haven't done anything yet, so I think I need to check with my internal teams and then get back to you if you do not mind.
Sounds good.
Yeah.
Thank you.
I still have a second part, so can I move on to the second one?
Of course.
Yeah. Okay. So after the presentation and the published paper with Meta platform, and I decided to continue the project. So the second part is the second is the continuing work, and the second part I'm naming the power envelope analysis for the thermal optimization of chiplet modules. The background I think I already shared in previous slide. So the next one is that we figure out there are more issues to be considered, and then we will the JCT will provide a solution. And then the next one, the final one, I will talk a little bit about the industrial standards and the calibrations. Okay, let me move on to the next slide. So, what are the issues? Here are at least a few issues to be considered. The first one is that how do we optimize the temperature distribution? If you look at the top two images, you will see that we use the power of the ASIC and the strength as a X and Y, and the left images we use the strength die temperature uh, to illustrate the the uh, the, the temperature of the strength. So, and the right image shows the same, but basically the Z axis is the ASIC die temperature. So with these two images, we can somehow we can determine the maximum temperature of the SRAM and the die. But the problem is that imagine that for a circuit designer, you guys maybe have to vary the power magnitudes. And if we have, for example, we have 10 dies, and the thermal simulation is going to be a big problem. Or maybe we will have to run thousands or maybe even hundreds or thousands of simulation. So how do we optimize temperature distribution efficiently? You try to. We should try to avoid doing too much simulation. So this is the first concern, and the second concern is that based on my understanding, different die may have different maximum allowed junction temperature. So again, this one, if we try to optimize the temperature distribution and optimize the power distribution, this is going to be very difficult. So this is the third bullet I mentioned about how do we optimize the power magnitude of so many dies. And then the last bullet is that is there a better approach for circuit designer to optimize the power distribution? And JCT, we decide to work on this one, and we are going to offer some solutions. So our solution is that we decide to construct a resistor power temperature matrix. Today I'm not going to share how do we construct that, but basically you can consider that we do a series of simulation, and for example, let me give you one example. Suppose we have 7 dies, then we input 7 powers, and then we can based on the junction temperature and we can found the accumulated junction temperature. We will be able to construct a resistor, thermal resistor matrix. And the good thing about this one is that we can vary the junction temperature. This is going to be very beneficial, especially, for example, the SRAM and the ASIC. If their maximum allowed junction temperature are different, so we develop a power envelope analytical approach, and we further the automatic. We develop an app to to automatically analyze the reliability of the module. Let me continue to. Oh, sorry, here I forget to mention. If you look at this equation, this one is not equal. So the analytical and then the analysis will be a little bit different. So let me give you one example. So this one we have 3 dies. So we construct a power envelope surface. If you look at the left figure, basically P1, P2, P3. If you look at this one, the 3 surfaces are the maximum allowed power magnitude. And suppose a circuit designer design power 400, 200, and 320 watts. Then we will be able to see that this set of power magnitude is outside of the power envelope surface. So it means that this set of power is not safe. So the mirror image shows that we calculate, I define it as a risk factor, which means that this one, the distance to the power envelope surface will be positive. Then it means that there's a risk. Okay, and then here, let me give you another example. So this one is, if you look at the left figure, the power is 150, 195 watts. And then with this approach, we'll be able to determine the distance to power envelope surface is below 0. So this means that this set of power is safe. So using this approach, this approach can be used not only to 3 dies, but also to 5 dies or 7 dies. Basically, it can be used. It's not limited by the die number. So with this approach, we can also define. If you look at this slide, we can determine the risk factor of each die. But sometimes the circuit designer they want to know the effective risk factor. So here I propose just one of the example. For example, we can use this equation to determine the effective risk factor. This slide I give you 2 examples. The left figure means that this power magnitude will be positive, then it's not safe. And the right image shows that effective risk factor is negative. Then it means that when the designer using this set of power magnitude, then it will be safe. So let me give you another. Okay, here I want to share you that we further design how do I call it? Maybe it's called automation calculator. So the designer can input the power and then also define the maximum allowed junction temperature. As I mentioned earlier, sometimes different die will have different junction temperature. And then after that, the designer can select a set of power. Then this tool will automatically determine the risk factor.
Oh, that's so cool. So I'm missing. I'm sorry, I missed the obvious. But how do you figure out the envelope? I thought that you figured how far you were below the envelope with your matrix. But how do you figure what the envelope is?
Okay, let me go back to this one. So your equation is how do we determine the envelope?
Yeah.
Okay. Um, okay, this is a little bit difficult to explain. So basically, if you look at this equation, right?
Yeah.
We have to solve this equation. And I mentioned that this one is not equal. It's basically it's less, right?
Right.
So you basically you need to solve this equation. So you can imagine that you know the resistor matrix, right? Thermal resistor matrix, the left one,
Right.
and you also have the temperature matrix. So basically, you solve this equation. Now you determine the power envelope, and this one is not equal. So it means just like this page, this image, it will not be. If it's equal, it will be these three surfaces.
And then given the design, you choose an operating point and you see how far below you are on that below the envelope.
Yes. Basically, for example, we select a set of power, right? Then we can calculate how far this set of power to the surface.
I see. Okay, so from the properties of the package, you see the envelope, and then from the operating point, you see whether you're at the envelope or below it, basically.
Yes, yes.
Okay.
For this one, we can only I'm only able to provide this kind of image. I mean, the three surface when they are only three dies. When they are more than four dies, more than three dies, then everything will be mathematically, because I won't be able to show you because you know the 3D I can only show you the 3D images.
Right.
So that's the reason I hear this slide and this slide. I'm only able to share you the 3D images. If they are more than 3D, then everything will be mathematical. Okay.
Thank you.
Okay, sure. So I already share you the previous. So this is another case that we have five. This one is 5 die, and then this one is 7 dies, and the number of the dies is not limited. And okay, I will share this one. And okay. So let me move on to the next slide. This one. So here I'd like to show you the advantage of this approach. So basically, I say that we shift the focus from the temperature to power magnetics. I would say that the advantage is that sometimes for the circuit designer, they they don't have any they don't have a good feeling of temperatures, but they have very good they because they need to design a circuit, so maybe their concern are more about the powers. So with this tool, they will be able to based on the power, they can determine the thermal reliability. And maybe this one, I'm not a circuit designer, but I think maybe this could be a good tool for the circuit designer, especially in the early stage of design. And another things I like to mention is that uh, for many electrical engineer, um, they want to know the thermal reliability ASAP without the need of a lot of thermal simulation. So these are the potential advantage of this approach. Okay, I think this is the last slide of my presentation. So I know that there are many companies working together to define a new UCI standard. And for me, I'm more a thermal and a mechanical background. My background is more thermal and mechanical. I don't know if there's a need for us to define a thermal coupling of chip lab die standard. I define it as a TCCD. Okay, so I don't know if do you guys think there's a need for us to work together to define a thermal standard? And there are lots of things we can do. For example, we can determine the measure allowed junction temperature, the temperature gradient, a lot of things. I just them two here. And if we are, I mean, the company, if we can work together, I think maybe we can figure out a way to optimize the die power of chiplet, and also a lot of the thermal electrical couplings. Okay.
So there's a group we have called the Chiplet Design Exchange Group. Do you attend those meetings by any chance?
Are you talking about the Wednesday one?
No, there's a Thursday one at 10 a.m. that
No.
basically they've actually it is definitely worth reviewing this talk there. They're doing, I'll send you a white paper they're putting together about power models for chiplets and everything else. It's kind of what you're suggesting is a sort of complementary to what they're doing right now.
Okay. I didn't attend that one, so maybe you can send me the link. I will try to join.
Sure. I will introduce you to the two gentlemen who run the meetings. It has fairly broad participation from EDA companies and other sort of semi vendors.
Yeah, I will be interested in joining. Yeah, I mean, the JCT definitely we would like to contribute. If there's anything we can do.
Oh, that'd be great. I think there's a if there's a white paper or something, the OCP would be very happy to publish it, I think.
Sure. Thank you. Okay, and the last slide is my contact. So if you have any question, please feel free to email me.
Okay. Thank you.
Sure. Thank you.
Any questions for Dr. Eric? Okay. Let me do my thank you.
Sure. Thank you.
And let me see. Let me do a quick round of opens. Any Tony Swami? Anything on your mind?
I think you mentioned about the spreadsheet, the update status of the spreadsheet. So are you going to talk about it?
Well, Shahab had to drop off. Actually there was some confusion on the logistics, which is why I wanted to have a quick update. They've settled on a metric for the comparison, and I think they're ready to sort of discuss everybody's files if they're available, etc. So I'll ask Shahab to please send an email on the common mailing list.
Okay. Thank you.
Thank you. Swami?
Nothing for me, Bobby. Thank you for the opportunity today.
Thank you for setting this up. It was a wonderful talk. Ravi, Mike,
Nothing from
anything
me.
on your mind?
No.
Michael?
Thank you. Nothing from me.
Kevin, Kash?
I think we're fine. Thank you.
Nothing
Okay.
from me.
JP?
Hey, Bobby, a couple of things actually. So, is the next week Mike and I are scheduled for the talk?
Yes.
Okay. Okay, I'll coordinate with Mike and then we'll put together something. And the other one is, I'm wondering if we'll be able to meet today this afternoon.
I think so. Let me. Yes, I think so.
Okay, I'll send the invite then to you and DJ. I don't know DJ is on the call, but I'll send him. And oh, hi DJ. Sorry, I didn't see you. I'll send an invite then. I just want to quickly sync up on our interop package.
Okay, sounds good.
Thank you, Bobby. That's it.
Mike, did you want to say something? DJ, anything on your mind?
Nothing on my mind.
Okay, Ali, Alan.
I'm good.
All right, then everybody have a good weekend and everything.
Thanks, Bobby. Bye.
Bye.
Thank you.
Thank you. Bye.
Thank you, Dr. Eric.
Thank you.